Hi there. I'm John McMaster here in my Silicon Valley garage.
Hey, and I'm Yusuf, back on Geek Moniker.
Woo! All right.
So, what do we have today for the audience, John?
So what we have today is, one of the questions that we get a lot is, we're very excited about microscopes, but there's a lot of really cryptic runes
Woo!
on the microscopes.
All
So
right.
the question is, how do you read those markings? What are all the numbers? How do they fit together? And how can we basically help people understand, like, what is it that they want on their system and how do all the pieces fit together? Does that sound about right?
Yeah, let's jump into it.
Let's jump in. Cool. So what I've got then, which I think will help guide the discussion a bit, is I prepared some slides with just a few images. And so I'm going to share those over. And here we go. Cool. And then hopefully you see something now that says stand by or something like that.
Yes, stand by.
Cool. I wonder if I can do this full screen. Unfortunately, Zoom is blocking the the present thing. You know what? We'll just roll with this. Okay. So what I was thinking we could start with is a little bit of talking about the origins of microscopes and kind of where we got today and why the ecosystems is, and talk a little bit about an RMS objective and kind of how this fits into the microscope ecosystem. Have you ever heard of an RMS objective? Let's start there.
I've not heard of RMS, but I've heard of objectives.
Okay, I've heard of objectives. Okay, so back in, I don't know the exact timeline, unfortunately, but the Royal Microscope Society, I guess in, England, UK, back in the day, there was kind of like a club, almost like the homebrew computer club, Silicon Valley, where there's people who are like, hey, these microscope things are pretty cool. Start making accessories for them. And they're like, wow, wouldn't it be nice if the microscope parts that I made on my system were compatible with the microscope parts that went on your system? And so after a little bit back and forth, they came on a combination of optical and mechanical standards that basically made it so if you made an objective for your system, we'll talk a little bit more about what that means, that'll fit together. So here's an objective, and unfortunately, I don't have a schematic of how this fits in to the greater microscope, but at a very high level, this is like the most basic precision lens you can think of. So there's that number that says 160 on that. We're going to focus in on that because that's where the magic really starts. And what that 160 means, can you see my mouse cursor here? I'll just kind of
Yes,
enunciate
I
that a little
can.
bit. So that 160 is the one we're going to focus on. And what that means is if you take this objective, 160 millimeters behind it is where the image will focus. So if you had,
Okay.
for example, your camera sensor, your eyeball, whatever it is that you want to use as your sensing element, you're going to get the best picture if it's 160 millimeters out.
Okay.
Does that make sense?
That does, and for people who may not be familiar with microscopes and objectives, maybe we can anchor this discussion down to, is an objective similar to the lens on a DSLR camera?
Yeah, I would say it's very much in the same spirit. There's a lot of concepts where they're really exactly the same. You'll hear, for example, F number, I think it's called in cameras, versus numerical aperture in microscopes. It's all the same concepts, just with different terminology.
Uh, Perfect.
Yeah, cool. Uh, and so this is like the most basic design that you could possibly think of. Basically, a lens, you have some distance back that you want a focal plane, and you either can put a more powerful lens or a less powerful lens. And as long as they all focus at 160 millimeters beyond that, you can all kind of swap between them. Does that make sense so far?
Yes.
Yeah. And so the second bit then is, well, how do you swap them? You need to standardize a thread. So they came up with this thread, which is called RMS thread now. And that is, I think it's 36 threads per inch, and it's something like 20.4 millimeter diameter, something like that. So if you cut some threads of that exact size, and I really don't know why that size was chosen, it honestly was probably some random person in the workshop, and that's carried forward today. There might be a fraction of an inch there. I don't really know. So now we have a basic optical and mechanical standard, so that if you make some part, it's going to be optically compatible and it's going to be mechanically compatible. And that really changed it because now we have interchangeable parts between these microscopes. And you can see, I have an example of the slide. I don't know the exact age of that microscope objective, but that's kind of what the older ones look like. In fact, I have one somewhere around on my desk that's like a 100-year-old objective. And here, actually, it's right here. So, so this is like a 100-year-old microscope objective, and I have put this on, some microscopes here, and it works perfectly fine. The images look great. It's mechanically compatible, and this is kind of like the mechanical optical version of like software compatibility, just never going away. And it's kind of cute that these still work, but at the same time, it's a little bit terrifying. Um,
So, that's interesting. Something that's, stayed around for like 100 plus years as a standard. Like, so is RMS of the most common standard out there, or is it being taken over?
It's dying a very slow, painful death. And we'll talk a little bit about why. And I know one of the things we talked about today is we're going to try to keep this very high level application focused and trying not to get too much into the nitty gritty. So it might really quickly get into the nitty gritty of optics design about why it's dying a slow death. But maybe a little bit later we can talk about we'll talk about infinity optics and why that's very slowly starting to displace that. But I would say let's use this as a starting point, talk about a few more of these numbers, and then we can go back to what I say the future of RMS objectives are. Does that sound
Great.
good? Cool. All right. So you can see these, basically the same. And let's go, a little bit further here. I mentioned that 160 is the gold standard, but basically over time, as microscopes got more complicated, people said, hey, I want to keep putting more accessories, in between the objective and the camera. So they said, well, with 160 millimeters, it's just enough for me to put the oculars, let's say, the things you look into, and for that to be ergonomic and stuff. So they said, well, let's add 50 millimeters, getting to 10 millimeters, so that way we can put some additional filters and stuff in there, and that's how you get this 210 over here. I think that's literally where that comes from. Is let's get a little more wiggle room to put some accessories in. You'll also see a few others like this 170 to the right, a little less common, but you do get other variants. I think that was Lomo maybe, which is kind of like an Eastern Bloc Russian microscope, had maybe 190. I'm sorry, that Lomo is 190. I think that 170 is not Zeiss, but one of the German microscope manufacturers. But 160 is really the most common, but just want to put out there are other objectives. So if you tried to mix and match these, for example, between vendors, you might be able to focus the image, but it's going to look really bad. You're going to have significant optical aberrations because you're really not creating the focal planes where they're supposed to be. So if that makes sense so far, let's talk a little bit about the evolution of RMS, and then we can talk a little bit deeper about some of the other markings we're glossing over so far on here. Sound good?
Sounds good.
All right. So one of the problems with this, of all of these incompatible objectives, it's kind of unfortunate. You want to use a specialty objective. You have to get it specialty made for like a Nikon or a Zeiss or Olympus. It just gets really annoying because everything's just incompatible and super kind of locked in. What if instead of choosing a focal length like 160, 190, 210, we said, let's focus the objective at infinity instead. And then we have something called a tube lens in the microscope that takes that infinity focus light and then that focuses it at a finite distance. So for example, the objective now is focused at infinity coming out of it. And then you say, you know what? I would like my optical path length internal to the microscope, not including the objective, to be 200 millimeters. So you can put a 200 millimeter tube lens, and because that area of the microscope is very well constrained, the accessories that you're going to put within your own microscope body, it doesn't really matter whether it's 200, 100, 300, because most users are not going to pull your microscope apart and put new giant accessories in there. They only care about the interface between the objectives, which they're going to swap out, and to the rest of the microscope. So this kind of change allowed microscope objectives to be a lot more industry standard, but now we've added the cost of that tube lens, because now you have this extra optical element internal to the microscope, but potentially also an additional element in each objective to now focus that to infinity, so it's compatible with the optical system. So you've gained a lot of flexibility here and interoperability, but you've unfortunately also increased the bill of materials cost per objective and per microscope a little bit. The plus side of this, though, is that it used to be really complicated if you wanted to put certain accessories into that 160 millimeter optical path, because if you rose up the head a little bit to stick some accessory in there, you now had to add compensating optics to re-stretch it to be as if you hadn't changed that optical tube length.
Right.
So some things get a little more complicated here, but it solves a lot of other problems. So generally, the industry has seen this as a win overall, even though it's a little bit more expensive and a little bit of growing pains.
Sure. Quick question, not
Yeah.
to diverge the conversation, but because you mentioned accessories so many times, maybe like
Yes.
what are some of these accessories?
Sure, yeah. So I don't know if I can easily pan over, but if you look at, for example, a more advanced microscope, let's just say like a polarized light microscope, for example, you might want to rotate the polarization of the light and then be able to filter it out. So, something as simple as saying, I would like to put in a Polaroid filter. If there wasn't a slot in your microscope path already for that, and maybe optical aberrations that the Polaroid filter is introducing, you might have to raise up your optical column to have an accessory slot to fit that Polaroid filter in. Maybe you
Sounds good.
also want to filter out some colors, and there's some more advanced ones, but I think that's probably a simple example to start.
Great.
Cool. So if that makes sense. Oh, and I was gonna say, and then this is why you'll still get, though, is a more of an entry level microscope. Like you might use in a high school biology class, like AM scope style microscopes. Those are still typically finite objectives because it's lower cost. So you still get decent optical quality, but you're not able to get as many accessories for those microscopes. So
Great.
cool. Okay, cool. So with that in mind, here is a sample infinity microscope. So you notice now, instead of saying, say 160 here, now you have the infinity symbol because it's focused at, a million millimeters, instead of focused at 160 millimeters, or something like that. And so one of the odd things, though, is, you see this is a 5x objective. Let's talk a little bit now about what does it mean to be a 5x objective. You'll see this is another 5x objective, but what if I told you these two objectives are wildly different magnifications? They both say 5x on them, but nowhere close to the same magnification. So why is that? Let's take a look at another comp here. You'll notice this 5x objective on the left has basically the same specs as the 10x objective on the right. And these are both Mitutoyo objectives. The left is from their, it's called Quick Vision System, I think, QV. And the right are kind of the gold standard semiconductor objectives. Now, one of the things you'll notice, we talked about tube lens earlier. So this F equals 200. That is the expected tube lens that this microscope will be used for. So to review, that's the infinity light is coming out of the microscope objective, and then it hits the internal components of the microscope. And now that's going to focus it to a finite plane so that it can actually form a real image. And so if you have an image that is further away versus closer, those are going to have different magnifications. So you'll notice this is a 100 millimeter tube lens, and this is a 200 millimeter tube lens. Because the second microscope system has it twice as far away, it's twice as large of an image. And that's why this is a 10x objective in that system, but it's a 5x objective in the other system.
Can you
Does that
explain what a tube lens is?
Oh, so tube lens is this concept of when we move to infinity optics, um, if you have light focused at infinity, it won't form a real image. Like you won't really be able to observe it. It'll just basically be blurry. So in order to get a focused image, you need to focus it down to something. And so you have to choose a distance that you would like to focus it at. Just like in the old RMS system, those objectives were focused at 160 millimeters. So you needed to have a camera sensor that was 160 millimeters away from that objective. In lieu of that fixed focus coming from the objective, the light comes out of the objective focused at infinity. But then in order to get a real image, you have to convert that infinity light to an actual finite distance, where it will actually, like I took my glasses here, you focus from the sun. So the sun is a great example. So the sun is light that's essentially focused at infinity. In order to get a real image, like when you look at the ground, you don't really see like a nice image of the sun, right? But if you take something like my glasses and focus it down, you're able to actually get an image of what the sun looks like. Does that kind of make sense?
Sure. So
Okay.
it's from the point where the lens in the tube focuses about.
Yeah, internal to the microscope. So it's an
Oh,
internal microscope component that is going to get you to form that image plane. So it specifies how far away is that image plane. And when you think of things like the lens equations from physics, if you've kind of gone through some of that, basically the further away you can put an image plane from a lens, the longer the focal length, the greater the magnification. So in this case, because we have a lens with a longer focal length, we get a bigger magnification.
great. Yeah, that makes sense now.
Cool. Okay, cool. Yeah, but because a typical user is not going to be familiar with things at this level, for convenience, they're marked with these sort of magnifications so to help relate them. And to close the loop on that, you can directly go from these markings, for example, and assuming your microscope is set up correctly, and if you know the pixel size on your camera, you can calculate the magnification of the objective for basically putting all of these together. If, for example, you have a 10x objective, and everything's set up correctly, that'll be 10x magnified on your camera sensor. So yeah, depending on your pixel size. Cool. Okay, so if all that makes sense, let's take a look at another example then with that in mind. One tricky thing here is that you'll also get some kind of random markings you have to be a little bit careful with. So this Olympus 5x objective, for example, on the left, you see this is f equals 180 and this is f equals 200. And I think these are some of the worst ones because if you're trying to calibrate the system, these are so close that they seem like they're both the same 5x objective, but there's actually a 10% error here between the two systems. And so you might, for example, have a system that's calibrated for one, think you're just swapping another 5x objective, and you might ask, where does this error come from? This doesn't make sense. So just something generally to be cognizant of as you're thinking about this. Cool. Let me see. I think I have. Okay. So I was thinking a next good topic would be wavelength corrections and how to read those, if that's a next good topic.
Sure.
Or we could talk about resolution briefly, maybe if that's maybe a good lead in. I know you said you didn't want to get too detailed into resolution, but maybe we can chat about that briefly.
Yeah, because these
Yeah,
are super in-depth topics, we could do like many videos on. But I
sure.
think it'd be good for people to know just like the high level overview of like resolution, right? Like and how that plays out.
Sure. And unfortunately, I realized I didn't have a side by side, but let's talk about resolution versus magnification. So what we have here is the magnification. That's how big something is. Um, but if you actually want to figure out how much information density is in there, you need the numerical aperture, which is this number here, 0.14. And basically, the larger that number is, the more resolution a microscope objective has. And this is directly comparable in cameras to, I always mix up these two numbers. I think it's the F number of the lens. So basically, how much, based on how much light the objective can collect, the more light, the higher the resolution. But at the same time, it'll also have a smaller working distance, and a lower depth of field typically. Um, so this one, for example, you see is a 5x, 0.14. If we look at this other set over here, though, you see a 10x 0.28. And so basically 0.28 means that, it's basically twice the resolution when we went from 5x to 10x. As you get beyond about 20x, though, the general trend is that it becomes nonlinear. It's harder and harder and harder to design a objective that will have the same resolution for each increase in magnification. So going from 10 to 20 still tends to be pretty linear. A 20x objective, actually maybe even already not linear. 20x objectives will be maybe around 0.42, for example, for Meditoyo. Whereas if this was linear, that would be 0.56. In fact, I have one here if you want to see that. See if I can get this on the camera. Maybe you can see that. Let's see.
No,
But
it's
yeah, maybe
super
a
tiny.
little hard to read.
Yeah.
But anyways, yeah. So and then so what starts happening then is you get what people call like hollow magnification. And the idea is that, if you have a signal and you kind of think of it like amplifying noise, you can always insert more, eyepieces that magnify the field bigger. But if in that initial step you didn't collect a image that had the fine detail you were looking for, you can continue to amplify that image and make it bigger, more magnification, but it won't have resolution. And that's where we have to be a little bit tricky as you go to higher magnifications, is are you actually getting resolution with those magnification increases?
Okay. So I guess a good comparison is between like optical magnification and digital magnification on your like cell phone camera.
Yes, that's exactly. With digital magnification, especially if you can't see the screen, maybe it's useful. Maybe, it can extrapolate a little bit, make it a little bit bigger, but you're not going to get more information. It
Okay.
may make it a little bit easier to see, but it won't fundamentally change the data that's coming out. So sounds good. Cool. Um, if that sounds good, let's talk a little bit about wavelength correction. So, and this is one of the things that I find interesting because this significantly increases the cost of the objective. Unfortunately, I didn't have a one-to-one to show like the dollar amounts between all of these. But there is, and so it's not fair because the objective on the right is a higher magnification. But there is like a 2 to 3 order of magnitude difference in price between the thing on the right and the thing on the left, even though they take up roughly the same amount of space. So let's talk about why that is. So the one on the left is a so-called achromatic objective. And, this is basically like, hey, I found some glass laying around. Let's make an image. And, it's kind of a good best effort. Let's see some data from the microscope. If you use that, though, you'll notice that, especially if you have a halogen light source, something with a high CRI, that the wavelengths won't all quite match up on the objective. And so we'll get chromatic aberration. And this can show up in a few different ways. The edges might be a little bit fuzzy. Even though you've got that, 0.17 numerical aperture there, you're going to lose resolution because of the spreading out of those wavelengths. And so there's different optical techniques to start improving on that. And the first really big one I think they started doing was they call like fluorite glasses or something like that. So, and I don't know the exact history, but in the original incantation of these objectives, uh, it was like fluorite crystals or something like that. Those were able to have some special optical properties that allowed you to kind of pair them up together and do certain lens combinations. And you would able to get something closer to a, quote, quote, perfect optical system. And by stacking this up and reduce those effects a little bit. Modern FLIR objectives, I believe, don't have those actual fluorite crystals or whatever, but they still mark them as FLIR to say, it's kind of in this correction category. The one to the right, though, is apochromatic. And that basically means more or less perfectly corrected asterisk, asterisk. I don't know if there's any, I unfortunately, I don't know off the top of my head if there's any standards for what it means to make a objective, apochromatic, but generally it means like you're not really going to see anything, at least with these three primary wavelengths of light. And that brings us to the fourth objective on the right. You'll notice how it calls itself an APO-VC. I forget what VC stands for, but it's very cool or something. I don't know. So that one is corrected, I believe, to 4 wavelengths. So another way to think about it is not only is this super high quality correction, it's corrected with kind of a higher CRI even than the other ones are, is maybe a way to think about it. Because even when you try to do this, there's still a lot of trade-offs. Some things are going to correct a little bit better, but the more points that you can, collect on that curve that are perfectly corrected, the better and better and better that you can get of optical corrections. So maybe take a step back there and see if any questions, thoughts, based on kind of that series.
And you mentioned like 3 or 4 wavelengths. Now, are there specific wavelengths they concentrate on, or it just depends on whichever manufacturer thinks matter?
I believe, and it's been a while since I've reviewed this, but what I vaguely recall is there's a few wavelengths that are like common. So I think there's like 550 nanometer light, like you can get a certain like green filter for example. And I think they've made sure that at 550, it's like really well corrected. And then if you go slightly outside of that, it might be a little less well corrected. And so the relationship between the M-plan APO then and the APO-VC is that they'll have more of those points where it's basically 100% corrected. And the in-between, won't be too far off, but the more points that you can add that are, 99% corrected, the better the spectrum you'll get, where the resolution is good across the board.
Great. You said M plan here. Is this a good time to move to like what those mean, what plan and M plan and L plan mean?
Yes, that is the next topic here. So let's talk a little bit about that. So we have these objectives here. And in a lot of biological applications, you want a cover slip. The issue is if you just try to look at some mushy biological system, you're going to have a very rough surface. You're going to have a meniscus on the water. You're going to have cells that are kind of flopping all over the place. And it doesn't give you very good images. So typically what you'll do in a biological system is you'll mount it on a glass slide, and then you'll put a glass cover slip to make a sandwich. And that sandwich really helps you to get good images because now you have a very well-defined optical interface that can peer into that watery solution. The problem with that, though, is that now you have to compensate for the glass you're looking for through, because the glass has very different properties, refractive index, for example, than air does. And so this number right here, so we talk about infinity, the number next to it, that's the cover slip thickness. And so what that means is that objective is intended to be used with cover slip of about 0.17 millimeters of thickness. And you can deviate a little bit from that, but it's optimized at 0.17. Compare that with these metallurgical objectives, the types that are used for semiconductor, and you'll see it says /0. And what that means is no cover slip. This is intended to be looking directly at your sample, like a rock or a silicon wafer that you typically don't put a cover slip on. Now, there are reasons why you might want to, but if you do want to do that, you might consider getting a biological objective. But it also turns out, and I don't have the fancy maths here, and maybe we don't want them for the purposes of this presentation. When you're at very low magnifications, though, it doesn't matter. Basically, the way that a lot of the optics works out is even at 5x, it more or less doesn't really matter whether you do cover slip correction or not. So once you get into the 5x range and typically below that, people say don't care. So that's what that infinity / minus is. They're saying like it's not even worth putting a cover slip spec on here because you're so far outside of the range where this matters that whatever, cover slip or not, you're basically going to get the same results. It could be thick, it could be thin. Basically, it's all the same. So this is kind of the range here then. So you have specified 0.17, specified as 0, no cover slip, or you're in such a range that it really doesn't matter. Cool. I'm trying to think. So I think that might be the core material. I can talk a little bit about what these numbers don't specify, if that's a good closing point to just kind of add to the thought cloud, unless you had another question or thought before then.
Like there are a couple of words on those objectives like plan and M and
Yes.
what do those mean? Because they seem to appear all the time in objectives.
Sure, yeah. So plan is going back to this of like the wavelength correction. Is how nice of a correction is this? So you notice the one on the left, for example, doesn't say plan, right? And I'm a little bit of rusty looking at the terminology on this, but I think that it basically a non-plan objective means achromatic objective. Versus plan means like it's the like the barrel distortion and these sort of things which we didn't really touch on too much is like how uniform is your field? Like do you get straight lines as you go across the objective? And so there's a lot more quality metrics than just the color correction, which is like this FLIR APO-VC. And in that same ballpark, I'll also throw in, there's a bunch of other metrics too, like the field number of the objective, which are not printed on the side. And the field number is basically like, okay, you have this specification on the objective. How large of an area does that quality hold for? And eventually you're just going to hit the edge of the objective. So, you're not going to see anything beyond that. But what is like a wide field objective, versus a narrow field objective? You want a large field number to see more of the wafer or the cell or whatever. So all of these play together because basically you could take even a lower grade objective and you could restrict the field number on that. And maybe it's apochromatic and maybe it's plan in just the center of that objective. But as you expand the field number where it gets more and more difficult to grind the lenses precisely, then the grading goes down. So it's basically a trade-off of, how wide of a field of view do you want and how well corrected do you want it to be specified within that field of view that you're allowing.
Very cool. Yeah, that makes sense.
Cool. I think, and then threading is the other thing that I'll add as a caution here. A lot of these objectives are all different threads. So this one, for example, these M-Plan APO, those are, I always mix this up, but I think that one is M26 by 36 threads per inch, a terrible mixed imperial
Hmm.
and metric unit. I believe that's literally from the RMS specification once again, which was 36 threads per inch. And they said, well, we want that, but bigger because, the field of view was too restricted, the field number. This one's, I think, M25. So, if you push really hard, you can kind of get these two to fit into your microscopes, but it's not really very good for it. So you don't really want to do that. So watch out there.
Sure.
Um,
John, we do have a question. I don't know if it's
oh yeah,
appropriate
sure.
for this talk, but somebody is asking if you could speak a little about the NIR/UV objectives.
Sure. Yeah, actually, let me, so basically we're done with this. Let me
Sure.
go to, I can do stop share.
Yeah, and
Sure.
specifically like what they use for, etc.
Yeah. I was gonna say I can actually demonstrate because I have such a system here. So let me grab a few from my magical tray here. Um, so here is a Mitutoyo uh NIR objective. And what you would use an objective like this, or the similar, there's like the UV objectives, is if you have a system like a easy laser, high-powered cutting laser, for example, these were really popular in the semiconductor industry. If you wanted to make holes in a material for microprobing, circuit edits and stuff like that. Similarly, because they need to be able to handle the very high power levels, whereas if you use a standard objective, it's going to absorb much more strongly in the case of the infrared objectives. And if it absorbs too much energy, it might actually damage the objective, and or you're just going to lose a lot of the power, especially for UV. Standard objectives just don't handle they're going to absorb a lot more power versus the IR and certainly the UV. The other thing too is if you start doing something like emission analysis, I think these objectives will pass about twice as much of the light as their non-IR equivalent. So you'll essentially get a lot brighter of an image. And in some of these fields, that makes a really big difference if you can get twice as much brightness, because your images will just look a lot better. You'll have shorter exposure times. And it goes back to also this idea of the wavelengths corrections, right? So if you have a broad spectrum IR source, for example, and you want that image to look sharp, if you take this objective, which was calibrated for the visible spectrum, it's just not going to look as nice in infrared, where this wasn't calibrated for. So I would say it's a combination of the spectral calibration, basically, and the absorbance at those wavelengths, especially once you get into the UV objectives, which I think this one, for example, instead of using leaded glass, which is what these are made with, this one is made of quartz. So this actually gets rather expensive quite quickly. So for example, I don't know what the MSRP on this one is, but the deep UV Mitutoyo 80X objective, for example, has an MSRP of $18,000, just as an example. And so it's just due to some combination of the very specialized materials, because normal glass can't pass a 266 nanometer light very well. And just the demand, because not that many people need an objective that can pass 266 nanometer light. Yeah, so anyways, hopefully that answers that. So basically making sure it can transmit the light, making sure it's well corrected at that wavelength. And especially once the powers are so high, like I'm using it in these cutting lasers, it can actually physically damage the objective if it's absorbing too much of that light.
Great. Yeah, Video Clown says, thank you for the explanation.
Cool. Cool. Yeah, so if that's good, I will add one final teaser. I'm going to put this back up real quick. You say for another time. So hopefully you can see these kind of few weird objectives that are left here.
Yes.
Cool. So I think maybe for another time, we will talk about some of the more advanced objective modes, illumination styles and stuff. So a little teaser. That's a solid immersion lens that I got on the left recently. I'm quite excited to play with that. And on the right are more advanced illumination modes like dark field. So I think these would be a fun topic, but I think probably out of scope for today. So I would ask for if you have any closing questions, comments, or if any of the viewers do. Otherwise, I would say that's probably a good stopping point for today.
Oh, we have one comment from Mango Man 667. He says certain grades of optical quartz can go for prices similar to gold per gram.
Yeah, like I said, I mean, we
Yeah.
could look this up real quick, like how much. So these guys, I impulse buy sometimes. I find them for like $100. I'm like, wow, I know this is an $8,000 objective, and I kind of have the equivalent that goes for it. But that's the converse side. I'm gonna say too, though, is the problem is these are so specialized that they're really expensive to manufacture. But without someone that really needs that, the resale value can just be awful.
Very cool. No,
Very good.
great explanation of like a super complicated topic. And if anyone's interested in diving deeper into these, let us know. We'll have some future videos on this at some time. But
Very
if
good.
not, is I guess this is a good stopping point, John.
Sounds good.
Awesome. Thanks a lot for everyone for tuning in. And yeah, just send us any comments or questions, and we'll try to answer them.
All right. Thanks, everyone. Take care. Bye bye.
Thanks. Bye.